Hi, so welcome everybody. Can everybody hear me? Would you say yes if you can hear me? Okay, so thank you very much. So yeah, so we're gonna continue. What we're gonna going to do today is to continue discussing about the compactness theorem. So as I said before, compactness theorem is one of the most important results in logic, and it has a big implications in an area of logic called model theory. For us, it will be the key step that allows us to allows us to invent or allows us to develop uh, some semi-algorithm for checking for first order logic. So it has an algorithmic implication as well. So some friend of mine who tried to connect topology and computer science, he said compactness is closely related to the computability in computer science. Okay, so let's talk about this a little bit more. So if I remind you about what compactness theorem say, it says that the one actor that appears in the compactness theorem is a set of formulas. So let's write this here. So we have a set of formula S that typically is an countably infinite set. So it has a formula F1, F2, and so on. And it's a countably infinite set. And we are interested in satisfiability of the formula. That means we are interested in finding one assignment for all the propositional variable such that it satisfies for all the Fi that appears in S. Okay. So this is, if you think about each Fi as a constraint, this means that we want to come up with A that satisfies infinitely many constraints. And then this theorem said the set of formula S, which is a typically infinite, is satisfiable. In other words, it has a solution if and only if for every finite subset of S has a solution. Every finite subset of S is satisfiable. And the interesting bit was, the one way to feel appreciate each theorem in mathematics is to understand why this theorem is non-trivial. And the reason this theorem is non-trivial is the following. You say that if we have a so if you have a 1A, the system is a bit strange. So if you have a 1A, that's set, so the left-hand side of this if and only if, say we have a 1A that satisfies everything in S. The right-hand side say if we take any finite subsets, like F1 up to maybe F3, there is a solution about this. And also if you take a different subset, there may be another solution about this. These solutions don't have to be the same, but just having solutions was assignment that make finite subset true for every finite subset somehow allows us to construct a solution for everything. Okay, so this is like partial problem. All the finite partial problem have a solution. This one has a say entire thing has a solution. And the theorem say that if we have a solution for any partial problem, that can be converted into the solution for the entire problem. And we said the non-trivial direction of this compactness theorem is this direction. That's because intuitively what it says, if we have a solution for everything, of course we have a solution for any finite subset. But non-trivial direction is going the other way. So this is a non-trivial direction. And for the proof that we looked at before, use some argument, which is a bit like a pigeonhole principle, and then we have introduced the notion of good partial assignment and so on. So there was some argument we used to construct, to show this non-trivial direction. And in fact, most of the application of compactness theorem, what matters is this non-trivial direction. And one application we talked about was that we are given countably infinite set of formulas And we want to come up with a semi-algorithm that proves non-unsatisfiability of this the countable set of formula, the given countable set of formula. So we want to come up with a semi-algorithm that takes S as an input. If it's unset, we want to return unset. If it's satisfiable, my algorithm may return set, or it may go to the infinite loop. And then we said, by using this compactness theorem, we can design such a semi-algorithm by as follows. If you take an infinite set of formula S, we just look at generate only its finite subset from maybe F1 up to Fn, check if it's unsatisfiable. If it's unsatisfied, we return it's unset. And if it's satisfied, we look at the next Fn plus 1, check it's unsatisfiable or not. So that gives us a procedure to show that this compactness theorem guarantees that if original formula is unset, our algorithm will always return unset. If original formula is satisfiable, our algorithm will go to the infinite loop. So that's why it's called the semi-algorithm. And then later, we're going to use this compactness theorem or its extended version for first order logic to come up with a semi-algorithm for proving, for checking unsatisfiability of first order logic formula, a theorem prover for first order logic. Okay, so this is maybe a bit confusing reminder of what we did before. Now, what I want, so here's some extra, today we're gonna mostly work on 3 problems that uses compactness theorem. And then the first problem is this one. Yeah, so it was an exam question by my colleagues, with James Worrell, who prepared this slide and gave this lecture. And then this was an exam question. So it was one of the 3 exam questions for 1.5 hour exam, 3 or 4. And then the question goes like this. So we have a countably infinite set of formulas. So we have a formula, propositional logic formula F1 of F2, and so on. So that's this countably infinite set of formula. And then we know that this, if you take a negation of these guys, so negation of F1, negation of F2, this infinite set becomes unsatisfiable, okay? And then, so that's one information that we have. Another information we have is that if you look at if Fn and Fn plus 1, there's always an implication between Fn and Fn plus 1, okay? So these are the information that we have. And from that information, this question asks you to prove some Fn should be a valid formula, which means that some Fn should be true all the time. So let me give you some more intuitions about what this you can think of this as a theorem, what this theorem actually tells us. For each of these Fi, we can collect all the assignment that satisfies Fi. So if you take all the assignment that satisfies Fi, so let's call it is a AI. That's so for each Fi, you can collect all the satisfying assignment Fi. Right. And then if you look this condition, Fi implies Fi plus 1. If I express it in terms of AI and An and An plus 1, what this condition tells us is that An is a subset of An plus 1. Because An is an assignment that make Fn true. And because of this implication, if assignment make Fn true, then it should make Fn plus 1 true. So this subset relationship is true. And that's exactly say the same thing as this Fn implies Fn plus 1 is valid. Now, unsatisfiability of so this unsatisfiability means that now imagine all the possible satisfying assignments. Okay, so this is all the possible satisfying assignments. No, not satisfying assignment, all assignments. And then this relationship, say initially we have F1, A1. Yes. We have A1, and then we have something larger, that's A2, something even larger, and A3, and so on. So it goes on like this. Okay, so that's the situation that's described by this formula, by this relationship. And the other relationship, which say that negation of Fn, there, if you collect all of them, that becomes unsatisfiable. What does that mean? That means negation of Fn, if you collect all the formula, and all the assignments that make negation of Fn true, that is the same as A, which doesn't satisfy Fn. That is the same as, it's an An's complement. Okay? And then if, I mean, this guys is unsatisfiable, means that intersection of all these complement is empty set. So that's what this condition is telling us. So what this condition tells us is like this. So then the picture goes like this. We have increasingly large set of AN. But then if you look at all these ANs, so there may be some AN and so on. Because this complement, I mean, AN's complement is empty set. That is saying the same as union of AN is the entire set. Okay, because I mean, if you remember what you learned from like high school, it's essentially some version of De Morgan's law. If you take a complement of this guy, that's going to be exactly this one. Complement of the entire set is an empty set. So this condition says the same thing as this. So the picture is you have a growing AIs, and if you take a union of all these AIs, that's cover everything. So that's the situation that's described by this theorem. And then the theorem say, if this is the case, there must exist some AN that's identical to the entire set. Okay? So you have a growing A1 becomes larger when you go from A1 to A2. A2 becomes larger when you go to A3 and so on. And it will eventually cover everything. If that is the case, then actually at some AN should be equal to the entire set. So that's what this theorem is telling us. Now I will give you 5 minutes to prove this theorem using the compactness theorem. So just imagine that you are in the exam and then try to solve this problem using compactness theorem. Maybe I will give you 7 minutes until 9:20. Of course, you can see the answer by just looking at the next slide, but I mean, I'm not going to check you. It's not a quiz, so maybe making some effort to try to prove this may help you to understand the compactness theorem and all the things that we learned so far. Okay, so let me show you how this works. Right. So yeah, maybe just using it this board is good enough. Yeah. So one thing we know about this compactness theorem is contrapositive. I mean the of the non-trivial direction, which say that S is on set implies there exists a finite subset S0 of S such that S0 is unset. Okay. If the entire thing is unsatisfiable, then some finite subset is unsatisfiable. Now, if I apply this compactness theorem, this contrapositive compactness theorem to the problem that we have on this side, so then we will instantiate this. Maybe just use red. We're gonna instantiate this with, I mean, no, not here. So we're gonna instantiate this with, I mean, these guys, which we know is unsatisfiable. So our S in this case is going to be negation of F1, negation of F2, and so on. So this is, we know is unsatisfiable by the assumption of the problem. And by this compactness theorem, then what we know is by the compactness theorem, we know that there exists some negation of F1, Fn is unset. Okay. Right. So if this is unsatisfiable and this one is unsatisfiable, I mean, any finite subset is, some finite subset is unsatisfiable, and you just pick the largest index of a formula appearing in the finite subset, then we can create this unsatisfiable finite subset here. So this is a unsatisfiable. So that what that means is a conjunction of F1 with negation, conjunction of negation of F2. This Fn is equivalent to false. So what we know is we have F1. If we take De Morgan's law on both sides, 2 Fn is going to be equivalent to true. Okay. So this is all coming from compactness theorem, non-trivial direction of compactness theorem, and then De Morgan's law. Okay. So now, sorry about this, I mean, the not very good organization of my drawing, the writing, but if we have something like this, now we're gonna use this second part, which is the Fn implies Fn n plus 1. What does this mean in the, if you write it as a, I mean, without implication, this means that we have F negation of Fn or Fn plus 1 is valid. And now, one thing we know is resolution lemma that we learned before. So the resolution lemma say, although when you explain the resolution lemma, we mostly focused on conjunctive normal form. The general idea of resolution or canceling some formula that applies to, I mean, any formula. It is any disjunction of formulas. So we're gonna apply the resolution here, this guy and this guy. So in particular, we're gonna apply resolution to negation of F1 or F2. Then if you apply the resolutions, the resolution will cancel this F1 term in both sides, and then give what we get is F2, so on, Fn. And the resolution lemma tells us conjunction of this, this coming from implications, this one coming from our compactness theorem. Their conjunction implies the formula that we obtained by applying the resolution. But now we know this is valid, which is always true. We also know that the other one that we obtained from the compactness theorem is equivalent to true, which means that it's always true. So that implies this guy is always true. Okay, this one is valid. It's coming from resolution lemma. And the validity of formulas used. And then we can repeat this entire process using what we have right now, and then next time we can use F2 implies F3, because F2 implies F3 will give us negation of F2 or F3. Then if we repeat the process we can get rid of F2. And we can continue to do so until we only have Fn. And what we get at the end is that Fn is valid. That's exactly the statement that's required by this question. Okay. And now if you clear our drawings. So the proof outline of the proof is given by, given here. That's exactly what I explained to you. And it uses compactness, De Morgan's, and then it uses inductions. But the key step of the induction involves using this resolution lemma. Okay, so we can prove something like this. And here's another application of the compactness theorem, which is about colorability. Okay, so we say that if we have a graph G, which is an undirected graph, so we have a set of vertex and we have a set of edges. And if we have this undirected graph, then we say that this graph is k-colorable if we can color each vertex with one of the colors from 1 to k, such a way that neighbors do not always get different colors. For instance, this is a valid color of this particular graph, because whatever edge you pick, the color between the two vertices are always different. But if the graph has an edge between these two vertices, then this is not a valid 1, 2, 3, 4 coloring of the graph, because these two vertices have the same color. Okay, and then this is another valid color for this graph with using 5 colors. So this one is, you can say, 5 colorable. And the original graph here is 4 colorable. Of course, the colorability doesn't mean we are using minimum number of colors. It just means that there is a way to color it. Okay. Now let's think about the following question, which is, imagine that you have an infinite undirected graph G. Okay, so this graph is infinite. It's a countably infinite. So there are countably infinite number of vertices and potentially countably infinite number of edges between those vertices. And then we are interested in whether we can color this infinite graph with say, k colors. K can be 3 or 4 and so on. And now the theorem said, if we happen to know that every finite subgraph of G is k-colorable, so that implies the entire infinite graph itself is k-colorable. Okay, so this say, to reason about the infinite colorability of this infinite graph, is sufficient to focus on only the finite subgraphs. But we have to make sure all the finite subgraphs satisfy this property. So that's what this theorem tells us. Every finite subgraph of G is k-colorable. So is this entire graph G. And then you can kind of feel that this has a flavor of compactness theorem. Compactness theorem is saying how it connects reasoning about the infinite object into reasoning about many finite objects. And this theorem says something very, very similar. And in fact, we can prove this theorem using compactness theorem in logic. So here's how you can do it. So we suppose that all finite subgraphs of G are k-colorable. So let me just put it into the right page so that you know what we are trying to prove. Okay, so this is a theorem that we want to prove here, and we're going to use compactness theorem. So to prove this theorem, we will assume that all finite subgraphs of G are k-colorable. And then under that assumption, we're going to, in a sense, encode this problem into the problem in logic, satisfiability problem in logic. Okay, so we will introduce countably many variables v, p, vi, which say that the vertex V has a color I. Okay, so PVI, this is a propositional variable which have a value either 1 or 0. If it has a value 1, that means vertex V has a color I. So I will be either 1, 2, up to K. V will be as many as the number, the possible V's are all the vertices in a given graph G. So there are infinitely many possible V, but there is, in this context, there are only finitely many possible I, because there are only finitely many possible colors that we are thinking about. So there are infinitely many propositional variable PVI, which means intuitively, if vertex V has a color I, and then we will design a bunch of formulas that express our problem using these variables. Okay. So we will introduce the 3 types of a formula: FV, GV, and HUV. FV and GV, we have a 1 FV, GV per vertex V. So there are infinitely many FV and GV. And we will have this HUV for every edge in the graph. Okay. And intuitively, what FV say is that vertex V has at least one color. So for FV is defined by disjunction over K possibility. And it says that there exists at least one I, one PVI, which is true. Okay, so this expresses that vertex V has at least one color. The second one, GV, the number of color for vertex V is at most 1. Okay, so this one, although it's written this way, I think, and this is by De Morgan's, this term is essentially the same as not of P, V, I, and P, V, J. So that means for for all ij, which essentially cover all the different colors ij, it's never the case that vertex V is colored with I and also vertex V is colored with J. Okay, so that essentially say vertex V has at most one color if it never have 2 or more colors. Okay, that's what this GV telling us. And now HUV say the HUV is talking about the vertex U and V, which are connected by edges. And this one, if I write it in this way, P, U, I, and P, V, I. That means that vertex U and V, which are connected by an edge, will never be given the same color. Okay, so that's what this conjunction is telling us. So FV say each vertex has at least one color. The GV say each vertex has at most one color. Then HUV tell us every pair of vertices connected by an edge should receive different colors. So that's all these 3 formulas are telling us. And then by using this formula, we can actually encode this colorability question into satisfiability question in logic. Okay, so if we take this infinite set of formula S, then this infinite set of formula S is satisfiable by some assignments. Then if and precisely when this infinite graph G is a K colorable. That's because from the assignments that satisfy this S, we can construct a coloring for all the vertices just by looking at this propositional variable P. Okay, if you look at the satisfying assignments for S and look at what kind of value it assigns to propositional variable PVI, that will tell us which color we should use to color all the vertices in the graph G. And for the other direction, if we have a K graph G is K colorables, so then from there, K is given. So K is given. So in the statement, K is fixed. So if the G is K colorable, from this coloring, you can construct a satisfying assignment. Now, here's now so this is a part of the proof, and now I want you to complete the proof. I will give you 5 minutes to complete the proof using compactness theorem in logic. Okay, so the proof is actually quite easy. So if you, so then so this is what we have to show. We need to show that this G is K colorable. K color. This is what we have to show. But by this theorem, to show this, but then because of this statement, it is sufficient to show to prove that this S, which is an infinite set of formula, is satisfiable. But by this compactness theorem, And we just need to prove every finite subset of S is satisfiable. Okay, so this is what we have to show. But if I look at a finite subset of S, the finite subset of S mean finite subset S0 of S will use only finitely many propositional variables. Okay, so we find such a finite subset S0, and then let the V is okay. So then let me erase this. So if you pick finite subset, then this finite subset will only refer to the set of variables, finitely many variables, because it's finite, like V0 up to Vm, the variables appearing in S0. So it's going to be appearing as a P V something comma I in S0. But for this subgraph, which only contains V0 and Vm, then that subgraph is K colorable by our assumption, because our assumption said all finite subgraph of G is K colorable. So if you go from here to here, but if you take a graph G restricted to V0 up to Vm, so this is a finite subgraph of G is K colorable. So therefore, we know that by this, essentially the same reason that we this if and only if it's true, and this in the part that I just ticked here, and because if it's K colorable, what we know is S0, which is a finite subset of S, is satisfiable. And then we are done, because this is by the compactness theorem. Okay, so just to recapture, to say it again, we need to show that G is K colorable, and because our encoding is good, it is sufficient to show that our set of formula S is satisfiable. By the compactness theorem, showing S is satisfiable is equivalent to showing every finite subset is satisfiable. And essentially proving finite subset is satisfiable is equivalent to showing the finite subgraph of G is K colorable. So it's all reasoning about infinite stuff to finite stuff via the encoding into propositional logic formulas. Okay. So it's not very difficult, but I thought these are quite interesting applications of compactness theorem. Right. So what I'm going to talk about now is going to be quite confusing to some of you, but I thought at least some of you learned topology and then heard about the compactness theorem in topology quite a bit. And then here we are talking about compactness. So you may be wondering what's the connection between the two. And here's a connection that I want to establish. So if you are not familiar with topology and so on, essentially you can relax for maybe about 15 to 20 minutes. And maybe you can just wake up, you can just take a nap and then wake up after 20 minutes. Also, but if you're familiar with the topology, hopefully you can get some idea about connections between compactness theorem in logic and compactness in topology. Also, if you are curious about these connections, somehow the word topology make you excited, then maybe paying some attention might help you a little bit. So the compactness theorem in logic that we covered is equivalent to the compactness theorem of particular so-called topological space, which is constructed using so-called product topology. I'm going to explain what it is exactly, sometimes this space has a name. I think it's called contour space. And this kind of space appears quite a lot in computer science. So when people talk about real number computability, this space also appears because it's a good space to capture what we mean by exact real number computations. And so on. So this appears quite a bit. Then it turns out this compactness theorems in topology is essentially equivalent to the compactness theorem in logic. Okay? And then furthermore, this compactness of this space is an instance of, although I put it as a question, it's called the Tikhonov theorem in topology. So I'm going to explain whole things a little bit. So give a quick crash course on topology, and then showing this connection. Okay, so right. Okay, so although maybe some of you know about topology, let me give you some reminder about what topology is. I mean, even if you don't care about these mathematics, if you're, for instance, interested in machine learning, if at some point you will learn about convergence of your algorithms, then one way to, the standard way to formalize the convergence is to put some topology, because it allows you to say when infinite sequence converge to some value. So you will hear quite a bit about so-called weak topology when you do some reasoning about the sequence of distributions there. So anyhow, so topology is so-called topological space. Is some set X together with its subsets. So it's sometimes written like this. And this, this strange O consists of subsets of X. So it contains one subset of X, and maybe it's better, X0, X1, X2, and so on. And they are all subsets of X. And it doesn't have to be, it can be finite, but sometimes it can be infinite, sometimes even uncountably infinite, and so on. Okay, so it's a subset, and it has to satisfy some conditions, which I don't want to talk about right now. So it has to satisfy some condition. Okay, so then this collection of sets here is called open sets. Okay, so it's a collection of open sets. And these open sets are used to talk about when things are continuous and what's the limits and so on. And now for compactness statement, to say the following, we said that the space X is compact if all open covers have finite subcovers. Okay, so what does this mean? This means that if you take a collection of open sets, so let's call it O0, which is a subset of O. So it's I'm taking collection of subsets, collection of open sets. If that take a union of every set in O0, if that's same as X, then there exists finite O1, which is a finite subset of O0. I think I make it very confused, abstract. So I will just show you the picture, which is much more understandable. So then this X0 in O1 will continue to be X. So what this one more intuitively says, we have a space X, and we cover this space by a bunch of subsets, open sets. So like lots of open sets here. and then maybe like this, and like this, and so on. I mean, here there are finite, but there can be infinitely many. Okay, and each of these open sets, for instance, one open set is this guy, and these open sets belong to O0. So we take a collection of open set that covers everything in X. So then if the space is compact, then we can always select only finitely many of those. That still covers the entire X. So for instance, we can erase many of these things, but still maybe, so we can erase quite a bit of that, but still maybe some finite collections. This picture is not very good, but some finite collections still covers the entire thing. Yeah, well, this picture is not very good, but this means if you take a collection of open sets that covers everything, there always exists a finite subset that covers, finite subset of this V0 that still covers everything. Okay. So we can kind of see that if you just look at these words. So this finite, you can kind of see that there's some connection between the compactness theorem that we studied, which also try to connect satisfiability of the entire set to satisfiability of the finite set. Okay, so now how does it relate to what we studied? And let me erase this. It turns out what we are studying, so the space that we are studying here, which is what we are studying in logic, is closely related to this space, which is 0, 1, n. This means that we take countably infinite products of 0, 1. So we are taking countably infinite products of these guys. So what this means is each element here is going to be an infinite sequence of 0 and 1. So 0, 1, 1, 0, 1, 1. So each element is an infinite sequence of 0 and 1. And it turns out we can construct a topological space. So this X and the notion of open set using for this space, which is underlying set. If you remember topological space, it has an underlying set X and then the set of open sets. And then in this case, the underlying set was 0, 1, and n. And then open set exact definition is a bit more complex, but they are, in a sense, generated from what I'm going to describe now. Okay. So this more technical term in topology is formal basis, but what I explained so far is essentially you can just state exactly the same requirements with respect to what I'm saying now. It doesn't change anything because compactness can also be phrased in terms of the base open set. So this case, the so-called open sets here, technically base open set, are always of this form, 0, 1. Just erasure. So it's always A0, A1, 2, AN. It's something strange. So this is not exactly the open set in this topological space, but it's as good as the set collection of all the open set. It forms a so-called basis. So in this case, the open sets looks like this, for A0, A1 up to, for some finite, the kind of prefix part for A0, A1 up to AN, you can pick any subset of 0 and 1. Okay, it can be 0, 1, or it can be something else. You can pick any subset of 0 and 1. And then for, actually, I was not quite right. So let me, sorry about this, I think. So we have, I mean, this one has always of this form, A times. And so this one, what it tells us is an A should be a subset of. Okay, so what this tells us is that because this is the infinite sequence of 0 and 1, all the infinite sequences, we pick some n, and then so for infinite sequence 0, 1, 0, 1, 1, 0, and so on, we pick some n. So in this case, some n may be 0, 2, 3, may 6. And for this prefix, we pick some subset. So for that subset, we may be interested in, I mean, this element, maybe another element is 0, 0, 0, 0, 0. Another is 1, 1, 1, 1, 1, 1. So these are three will form my subset A. And for the rest, we said it can be any sequence of 0 and 1. So that's what this is, I mean, subset of, I mean, this set actually look like. For some prefix of size n, we pick some specific set. For the rest, we say it can be anything. Okay, so these are some subsets of this space. Then this subsets can, if you collect all of them, that form essentially the collection of open sets. And this is called, I think it's called contour space. And it turns out this space is a compact. By Topological theorem. And that is related to exercise 3. That's an answer for exercise 3. So more precisely what happened is that this space of, I mean this, if you are familiar with Topological theorem, I mean, if you consider topological space, which contains only two elements, 0 and 1, open set is everything, so-called discrete topology. And because it's a finite set, I mean, this is a compact space, and this space that I just described is essentially a countable product of compact space. So then if the Tikhonov theorem said this countable product is again compact. Okay, so I started, so let me just finish it. I feel like I'm losing everybody, so, but let me just finish. Just bear with me, maybe about 7 more minutes, then I'm done. Okay. So this is that, I mean, the specific compact topological space. It turns out what this space is essentially identical to what's really happening in logic, propositional logic. And how you can view this, the way you can view this is, if you have this infinite sequence of 0 and 1, you can view this as an assignment that we talk about, where this P0 is a value of propositional variable P1. This number 1 is a value of propositional variable P2. This is a value of propositional variable P3 and so on. Okay. So this infinite sequence is, we are fixing the particular order of countably many propositional variables. And this infinite sequence provides, I mean, it's essentially identical to setting some assignment to all the propositional variables. And if you view it this way, and then the compactness theorem, let me just show you the first. the compactness theorem in logic implies a compactness theorem for, the compactness theorem in topology implies a compactness theorem for propositional logic. And now imagine so to prove this, we are considering a countably infinite set of formula, F1, F2, Fn, so on. And the non-trivial direction of compactness theorem say if S is unset, then there is some M such that F1, Fm is unset. Now let's try to understand this unsatisfiability using the infinite, so assuming that we have a conjunction and disjunction for that works, that can be applied to infinitely many formulas, okay? That we don't have such a thing, but that will help you to understand the connect with the compactness. So this S is unset means that if you take all these Fi, take infinite conjunctions. Sorry about this, I somehow. One, two, infinity. So say that this is unset, which means it's equal to false. Okay. And then this the right-hand side say Fi, I is 1 to M, that is equivalent to false. Now, if you take a negation for everything, although we never talk about infinitary conjunction and infinitary disjunction, by the De Morgan's law can be extended even when we have this infinitary conjunction. So if you put a negation for both sides, this one say the same thing as I on infinity negation of Fi, that is equivalent to true. And we put a negation there. Equal to true. Okay. So this non-trivial direction of compactness theorem is equivalent to saying if we have infinitely many formulas, if we negate all of them, and then take their infinitary disjunction, if that is equal to true, that means there exists some finitely many Fi's. If we negate them and then take their disjunction, that should be equal to true. Okay, so that's a non-trivial direction of compactness theorem. Now we're gonna rephrase this as a compactness in topology. What we can do is we can change each of these negation of Fi as a each of these Fi as an open set. So each of negation of Fi will become an open set. And then equivalent to true, this means it covers everything. So more precisely, equivalent to true means it covers 0, 1 up to n. And this one also means it covers 0, 1 up to n. And I said the compactness, say, if you have a collection of open set that covers the entire space, there exists a finite subcollection that will cover the space. So that's exactly the statement of the compactness theorem. And now how can you view this as an open set? One may, as I show in the exercise I showed you, you can think about assignments that satisfy negation of Fi. And this assignment, because Fi only uses finitely many propositional variables, this set of assignment that satisfy negation of Fi will have the form. So I use A there, so maybe some. So we'll have the form like this. That's because if Fi only uses a propositional variable P1 up to Pk, then for propositional variable from P1 to Pk, this formula negation of Fi says something, so we have to be careful about their assignments, but all the rest, it doesn't really matter. So the assignments will have the form for P1 of the Pk. It carefully assigns something, all the rest, it doesn't, it assign anything. So that exactly corresponds to formula, like, saying this A have this form where this B part only is a, okay, so where this B part is a subset of 0, 1 to K. Okay, because for the first K propositional variable, we have to be careful. Otherwise, you don't have to do anything. And if you see this one to what I wrote over there, that's exactly, this is the form of the open set that I told you before. That's exactly the form of the open set. So if we have a propositional variable and the collection of formulas such that if it's unset, if you take the negations, then each of the negation will become an open set. And this disjunction corresponds to the union. So it means the union of these open sets is equal to everything, which is it means that a collection of these open sets will cover this entire thing 0, 1 up to n. And then now the compactness in topology, say actually you can find the finite subcover. So that finite subcover gives this F1, this finite subset F1 up to Fm, which satisfies this condition. Okay, so I think if I go further, I think some of you may become intolerable to some of you. So I hope at least it gives some idea about how things are going on in logic is related to what's going on in topology. And you can actually show the other direction as well. Okay, so from the compactness theorem for propositional logic, you can also prove compactness theorem, compactness of this this particular space is 0, 1 to the power of n. Okay, so that's here. Right, let's move to sum up. So here's the summary of what we covered so far. So so far we covered about the syntax and semantics of propositional logic, and we studied about various normal forms. So we discussed about DNF formulas, CNF form, and also we discussed about some special formula like Horn formulas and so on. And then for these specific kind of formulas, we studied about their this algorithmic property. We said Horn to CNF, XCNF, there are polynomial time algorithms to check their satisfiability. General case, we studied about algorithms which show the satisfiability or unsatisfiability in the general case, which those algorithms were based on resolutions, and we look at variable elimination algorithm and DPLR algorithm. Finally, we studied about compactness theorem, which is a bit more theoretical result about propositional logic. And now we have about 5 more minutes. So what I'm going to tell you is that some story, and then I will finish, okay? So next topic that we're gonna talk about is a first order logic. And then maybe I will tell you some story about first order logic. So the inventor, the person who invented, so first order logic is something, if you want to formalize mathematics in logic, you need a first order logic. Propositional logic is mostly about studying connectives, but it's not very expressive to kind of encode many interesting statements in mathematics. So in fact, the famous logicians around the 1900s, they were very much interested in formalizing mathematics. And one of the leading figure is Frege. So, I mean, you might heard about Russell's paradox, and that's all start from Frege's effort to formalize, put mathematics on the solid foundation. He want to have some basis of arithmetic, which is as solid as what people did in geometry. Okay, and then so he came up with the books. So I heard he wrote one book which is mostly about logic, and then he used his result in his book to kind of formalize arithmetic in mathematics. And this is some of the notation and then in that book he introduced essentially what nowadays called second order logic with identity. But the big inventions that he did was to invent universal existential quantification into the logic. Okay. So some kind of side story I want to tell you is that this is the notation that that the Frege used. And then so this notation looks very different from the typical notation that you see in logic. So looks like, this notation looks very weird, but this was the notation that Frege used to express implications. GA implies FA. So I don't think many logicians actually knows about Frege notation. So if you remember a little bit, you can kind of meet your friends who major in logic and say, okay, this is a kind of basis that every logician should know, and why you don't know it. So you can make fun of him. Okay, so this is an implication in logic. And another notation that Frege used is this one, that's a universal quantification. So this notation say for all A, GA implies FA. So Frege used, in a sense, like a two-dimensional notation of logical formula. And I think his kind of notation didn't really survive, but some of his notation survived. So at some point, some students ask me why we are using these notations when we talk about logical entailments, say, formula F entails formula G. And that's because this notation is actually coming from Frege. I think this vertical bar and this horizontal bar means something. So I think vertical bar is like a deduction or something. So this means something, and then that's invented by Frege, and this notation is actually coming from Frege. Okay, so this is not a very interesting introduction to first order logic. We're gonna talk about first order logic on Wednesday. Okay, so thank you very much for attending today's lecture, and I'll be here for 5 more minutes. So if you have any question, feel free to ask me. Okay, that's it for today.